Okay, welcome back, everybody. Yesterday we ended with our first example of what we could call forbidden subgraph results. So, just to remind you what that looked like. What we refer to as a forbidden subgraph result was the following. The theorem in question was if G is two connected, we'll see soon that being two connected is actually required for being Hamiltonian. So this assumption isn't much in terms of, well, it isn't much or it's everything, depending on how you're looking at it. Since if you want the graph to be Hamiltonian, two connected is not an option. Um, so it will be two connected. So anyway, it was if G is two connected and it is claw free, that is, it does not contain this complete bipartite graph K13 as an induced subgraph, and Z1 free, so this is another naughty induced subgraph that is disallowed. So if it is free from both of those, if it contains neither of these as an induced subgraph, then it is Hamiltonian. That is the result. So let's see first how this, first of all, like what forbidding an induced subgraph, a particular induced subgraph does. All right, so let's see how we would prove this. I'm going to restate this theorem so that we can have the proof here all on one page. Here's this theorem. If our graph G is two connected and it is claw free and Z1 free, so this is K13 and Z1 free, then it is Hamiltonian. What, of course, led us to this in the first place was our consideration for what sorts of things we could impose on a graph to force it to be Hamiltonian. Okay. So this is in a class of results. We call this forbidden subgraph business, where we ask, well, can we forbid certain subgraphs or certain graphs from appearing as induced subgraphs to force Hamiltonicity? You might ask, is it okay to, say, impose one of these and not the other? Well, we'll see why for this theorem both of these are needed, and we can't just forbid the claw. There's going to be a bunch of results we talk about right after this, but I wanted to give a proof that shows how these forbidden subgraph things show up, or how it can be used to actually do this proof. So suppose G is as above, right? So suppose G is as above. That is, it is two connected and K13 free, Z1 free. Okay, so it doesn't contain either of these as an induced subgraph. Okay, I've made a big deal this whole time making the distinction between subgraph and induced subgraph. I'm going to really hammer that home when we talk about these examples, because certain counterexamples to certain facts wouldn't function as counterexamples if we talked about merely subgraphs and not induced subgraphs. So there's absolutely an importance of distinction here. Okay, so let G be as above, and let C be the longest cycle in G. Now, here's the thing. How do I know that a longest cycle in G exists? Well, G is a finite simple graph. If it has a cycle, then it has a longest cycle. Okay. Well, what if it doesn't have a cycle? What if it is acyclic? Is that possible? This is actually exercise 14 in section 1.1.2. Which says that every two-connected graph has a cycle, at least one. So if you are two connected, you are guaranteed to have at least one cycle. Okay. Now, of course, this C, this longest cycle, maybe it's a cycle in G that spans the vertices of G, in which case it would be Hamiltonian. It would be a Hamiltonian cycle. G would contain a Hamiltonian cycle, and thus G would be Hamiltonian. But if that's the case, then we're done. We're happy. So let's say that it's not, right? So suppose C is not Hamiltonian. But being not Hamiltonian means that it can't span all of the vertices of G. There has to be some vertex in G that is not in this cycle. Okay, i.e., there exists some vertex V that is in the vertex set of G such that V is not in the cycle C. Okay. But with V adjacent to a vertex, say W, that is in C. So, let's ponder for a second whether or not this is guaranteed. Must there be a vertex in G that is not in the cycle if C is not Hamiltonian? Well, yes, that's the definition of not being Hamiltonian. It's failing here to span the vertices, right? The definition of cycle, of course, means it can't repeat or anything like that. So the fact that it's a cycle already, it not being Hamiltonian, it means it doesn't span the vertices. So there has to be one that's not there. But does there have to be one that is not there that is adjacent to a vertex that is in the cycle? Well, this is where the two connected bit comes in, right? Because this is telling us the minimum size of a cut set of the graph. Okay, so if it were not, then G would not be two connected, right? So there has to, it is in G, it is adjacent to a vertex that is in C, while V itself is not in C. That is what we are guaranteed here. Okay, so there's at least one of these. So we have V and W. Now, let A and B be the immediate precursor and successor of W on C. Meaning that the cycle C looks like this, right? Whatever it looks like. Right, here's a representation. It's going to close up eventually, but whatever this looks like, here is our W. We'll let A be the precursor and B the successor of W here. And so here's my cycle C, my vertex V, which may be connected to other vertices in G, of course, but I'm not purporting that what I'm drawing here is a complete graph of G, but there is at least adjacency between V and W. And so we call A the immediate precursor and B the immediate successor on C respectively. of, of this vertex W. Okay. Now, the question is either A or B adjacent to V? So, can we have an edge here? Can we have an edge here? Well, the answer is no. No to both. Neither of them are adjacent. Why? Let's suppose that they were. Suppose that they were. So in this picture, suppose I fill in this edge. Well then, now I can form a cycle, call it C prime, that whatever it does outside of this picture is irrelevant, but when it gets to this part of the cycle, it goes from this vertex to A, from A to V, from V to W, since we know V is adjacent to W, then from W to B, and it proceeds as usual after that. We could make a C prime that is still a cycle that is longer. The length of C, whatever it is, if I replace traversing this edge, A to W, with going from A to V and then V to W, that increases the length of C by 1. So, right? So if so, we could construct a cycle, we'll say C prime, with greater length than C. Which would contradict C being the longest cycle. Okay. So, so this is not possible. Because it's not possible? No, neither A nor B is allowed to be adjacent to V. So they are both non-adjacent. Now, the question is A adjacent to B? So here's my second question. So, question, is A that is, can I fill in this edge here? Is that possible? Well, if it is not, right, if A is not adjacent to B, then, so if not, then the subgraph of G induced by the vertices W, V, A, and B is what? So if A is not adjacent to B, what does this induced subgraph look like? Since A and B are not adjacent to V, if A and B are also non-adjacent, what does this subgraph look like? Here's W. Here's V. Here's A. Here's B. Because this is an induced subgraph, it means that when you induce a subgraph from some set of vertices, you take all of that set of vertices and all of the edges, both of whose endpoints are in that set of vertices, right? So this would contain no other edges because there's no adjacency between V, A, and B, right? So V is not adjacent to A or B. A and B are not adjacent either. So if not, then the subgraph of G induced by WVAB is this. But what is this? This is the claw. So that's not possible, right? So this is impossible, right? So that can't happen. If so, then subgraph of G induced by WVAB is one where, so V is not adjacent to A and B, but A and B are adjacent. So I'm going to draw this graph as follows. Here's V, here's W, here's A, here's B. But what is that? What does that induce subgraph? It's Z1. So that's Z1, which is also not allowed. So we have reached a contradiction here. Now we have to trace back through. What is the first thing we said that was basically an assumption? What is the first thing we did, right, that is an assumption beyond what we assume here? We suppose that C was not Hamiltonian. And so C must be Hamiltonian. This longest cycle in G, when G is 2 connected, claw free, and Z1 free, it has to actually be Hamiltonian. If C is Hamiltonian, well, it's a Hamiltonian cycle in G, thus G is Hamiltonian, since it contains a Hamiltonian cycle. And that's that. So you see very directly how these forbidden subgraph results can be proven and how the forbidden nature of those subgraphs is used directly in the proof, right? So that is how this works. This is a good example of how to use the fact that a subgraph is forbidden. Okay, here are some other facts. So here's a fact. Every Hamiltonian graph must be 2 connected. So two connectivity is required for Hamiltonian graphs. So you will prove in your next homework, you will prove that every graph G with connectivity of G equal 1 cannot have a spanning cycle. Okay. Okay. Next theorem. Let G be a claw-free, and this graph N, I'll flash it on the screen again here in a second. Free graph. 1 if G is connected, then G is traceable. Look at yesterday's lecture for a definition of traceability. Right, this is directly related to Hamiltonicity. And 2, if G is 2 connected, then G is Hamiltonian. I'm not going to prove this. This was proven by Duffus, Gould, and Jacobson. This is another nice forbidden subgraph result. I promised I would put N back on the screen. So the 3 that we talked about first are the claw, Z1, and what we're calling N here. Notice how it is arranged. Okay. So the claw showed up in both of these forbidden subgraph results. So you might immediately notice that, oh, well, one of them involved this forbidden subgraph Z1, another involved this forbidden subgraph N, but the claw was actually in both of these results, right? It's not a coincidence. The claw shows up in many of these results that have to do with Hamiltonicity involve the claw in a way. So it is somehow striking at like what is essential about the property of Hamiltonicity. So this shows up a lot. So note claw-free graphs are important for many Hamiltonicity results. Lots and lots of different things. I can't possibly summarize all of the stuff, so I think kind of following the textbook here and giving a nice smattering of some open problems here to kind of illustrate what it is that's going on. So we're going to move on next. Something you don't very frequently get in your math courses or in many courses period is just a statement as part of the course in terms that are completely understandable in terms of the course. You don't need any other info than what we've already defined, plus the few terms that we're going to define coming up here to understand these problems, and yet they are open. So now, on to some open problems in graph theory. So the first type of open problem I talk about is going to concern something called detour paths and their intersections. So I use the word detour informally in prior lectures where we were talking about stitching in Herholtz's algorithm or stitching in a cycle. And I called it a detour in the sense of it's an intentionally longer path. It's not entirely inaccurate, but it's going to have a precise definition here. So given a graph G, the detour order of G which we are going to denote tau of G, is the number of vertices in a longest path in G. If any path P has the same number of vertices in it, we call it a detour path. So we are, right in the definition, we're acknowledging that these need not be unique, right? There may be several longest paths in G having the same length, right? So if a path P has tau of G vertices, we call it a detour path. So previously, as I said in a couple of the examples, when I was just using the English word detour, I meant basically any intentional lengthening of the path that you were on. But now and henceforth, whenever I talk about detour in this sense, I'm going to specifically mean this notion of detour. So this is what I'm talking about. So a detour path is one that has the most vertices that it can have as a longest path in G, right? Okay. Now, again, in homework 1, I don't think this problem was assigned in homework 1, but I might be forgetting. But in exercise 8 of section 1.1.2, you were asked to prove if G is connected and P1 and P2 are detour paths, then the intersection must be non-empty. So if G is connected, P1 and P2 are detour paths, so they are two possibly distinct paths that are the longest paths in G in this sense, then they must have at least a point in common. They must have at least a vertex in common. The intersection vertices of P1 and P2 must be non-empty. Okay. If, like I said, I'm not looking at the homework assignment at the moment, so maybe I didn't assign this, but if I did, hopefully you saw that it wasn't too hard to prove. If not, this isn't too hard to show. I mean, it better not be, right? It's in one of the first sections, so this is some of your warm-up stuff. Okay, so now the following question is this exercise asks the question for 2 detour paths, but what about 3 detour paths? So if G is connected and P1, P2, and P3 are detour paths in G, then must each intersect in at least one point. So must their vertex sets, all 3 of their vertex sets, have a vertex in common. This is an open question. I checked around a little bit. The textbook was written in like 2008, I think, is the edition that this textbook was written in. So it was unsolved as of 2008. I went looking, went digging around, and it seems like as of this year, this is still unsolved. I might be wrong. There are some partial results. I read a few papers from from the 2020s that were either related results or partial results, but I couldn't find an actual full resolution of this. So this is still an open question as far as my knowledge is concerned. If you can find a resolution to this, you can let me know. But as I said, I didn't. Quick look yesterday. I don't think that this has been resolved yet. So this originally came from another question. So the origin of this was another question from Galai in 1966, which was, is it true in every connected graph there's at least one vertex that lies on every detour path? Which I'll just write here. So is it true that in every connected graph there is at least one vertex that lies on every detour path? This original question, the answer was found to it, and the answer is no. This is too much to require, so the answer is no, but the example, the first example anyway, was due to Walter, so counterexample. This was 1969, I think, was when this counterexample was cooked up. There it is. So in this example, the detour order of this graph is 21. That is, 21 is the longest, or it's the longest path. It's the most amount of vertices the path can have in it. Okay. And every vertex is missed by at least one of the detour paths. So every single vertex here is missed by one of these detour paths. So no, there does not exist a vertex that lies in every detour path. Okay. So, okay. Well, is there an easier example? And the answer is yes. A few more years later, here's another example of this. This graph has 12 vertices. It has detour order 10, and every vertex is missed by at least one of the detour paths. So again, that intersection is, well, it's not always going to be non-empty. Right? In fact, there's not a single vertex that lies on every detour path. Okay. Now, you see why every detour path, requiring every detour path is too much. What if we talk about it for a list of distinct detour paths? That's what we did here in the case of 3 detour paths. This is still an open question. We could ask the more general version of this question, which is also um, somewhat open, well, in certain cases. So here's a related question. So if G is connected and P1 to Pn are distinct detour paths, so they have the most amount of vertices in G, must the intersection of all of these vertex sets be non-empty. So notice this is the same as our open question here if n is equal to 3. Okay, so we know we can't have a full answer to this, because if we did, we would have the answer to the previous question. So we also know that for n equals 12, the answer is no. This is due to an example provided in 1975 by Schmitz, which is the following. Here it is. There's the example given by Schmitz. As you can see, the detour order of this graph is 13. You can find your favorite detour path here. There are exactly 7 detour paths. You can find any 7 of them if you like. And every vertex of the graph is missed by at least one of these paths. So this tells us that for n equals 7, the answer to question B is also no. Okay. Sorry, I mislabeled these things. The answer is no for n equals 12 by our previous example. Sorry, here. Okay, so the 1975 Schmitz example shows that for n equals 7, answer is also no. Okay. Okay, so that example that I just showed in the book is the n equals 7 case, where there's 7 detour paths and all of them miss at least one vertex. So 7 is the highest, is the smallest number for which we know this is definitely no. The question is, what about the others? So, but the question is open for n equals 3, 4, 5, and 6. The current we'll say thought, and again, there may be an improvement on this that I missed when I was looking over the literature to see if there had been improvements made. The general consensus, I would say, is that it seems to be true for n equals 3, more shaky on these 4, 5, and 6. More shaky if there just might be an example here that that just hasn't been cooked up yet. But who knows? It could be true for 3, 4, 5, and 6. But for now, the n equals 3 anyway is just a conjecture. But this is actually open for 3, 4, 5, or 6 detour paths. This same question is open. So there's our conjecture. If G connected, then the intersection of any three detour paths is not empty. It's unknown. You can make a name for yourself in the world of graph theory if you were to resolve this. So it's actually extra credit in the homework for this section. If you can solve any of these open problems, I'll give you extra credit. So that's one sort of open problem you can consider. Now let's get back to Hamiltonicity questions. So returning to forbidden subgraphs. It has been shown that if G is too connected, then G being claw-free and we'll say W free, where I haven't defined what W is yet, being claw-free and the path on 6 vertices free. Let's do Z2 here. All of these imply Hamiltonicity. Of G. What is, you know what the path on 6 vertices looks like, right? There it is. What is W? W is this graph. So I'm going to give one representation of it anyway. There's W. And Z2, you'll see why it's called Z2 in a second. You just tacked on an extra edge to Z1. So combining this with our other results, remember we had our previous results that being claw-free and Z1-free did it. Being claw-free and in-free also did it in a two-connected graph. So you will notice that, and just reminding you here, right, of those other results, there was the statement that if G is two connected, claw-free and in-free, then it's Hamiltonian. Here's a reminder of what in is. And our first theorem on this, which is if G is two connected, claw-free and Z1 free, then it's Hamiltonian. So in every single one of these, the claw shows up. Well, 1997, it was shown that this was not merely a coincidence. So this is a result from 97 due to Faudry and Gould. So here's the theorem. If being RS free, where RS are connected and neither is the path on 3 vertices, so where RS are connected and neither is P3. If being RS free implies that a 2 connected graph is Hamiltonian, then one of RS is the claw, which is K13, and the other is an induced subgraph of one of the following: the path on 6 vertices, Z2, W, or N. The reason we're including this language of induced subgraph, also we don't have to mention Z1 here, since Z1's an induced subgraph of Z2. Right, here it is. Right, so there we go. It's an induced subgraph of one of these things. Okay. So, this says that basically any result that you find on these forbidden subgraphs are going to have the claw in them. So that is why it is showing up. It is because it's like an essential thing for these forbidden subgraph results. It's telling you a lot. Now you might ask, like, how essential is it? Right? Is it so essential that being claw-free alone is enough to guarantee Hamiltonicity? And the answer is no. So maybe I'll ask the question still first anyway. If G is, say, 2 connected claw-free, is it Hamiltonian? And the answer is, maybe I should say, is it necessarily Hamiltonian? To make this really pop here, the answer is no. In fact, the only single graph, only forbidden subgraph that will work to do this is P3. So in 2 connected graphs, the only forbidden subgraph that is strong enough to forbid on its own to imply Hamiltonicity is the path on 3 vertices. Okay. Notice the path on 3 vertices had to be specifically excluded in this theorem because that would again make this theorem statement awkward. Excluding P3 implies Hamiltonicity. Again, there is an exercise that you will investigate when it comes to this. But what about, so just forbidding the claw is not enough, but what if we forbid the claw but up the connectivity? So instead of being 2 connected, it's like 3 connected, or 4 connected, or just some higher amount of connected. So that leads to the following natural evolution of this question, which is the following. So question: if G is claw-free and K connected, where K is greater than or equal to 3, must G be Hamiltonian? It turns out that for K equals 3, the answer is no. To see this example, here is an example of a 3-connected claw-free non-Hamiltonian graph. So this is 3 connected. You can verify that pausing the video and looking at it. All right. Claw-free and non-Hamiltonian. So here is where the bit comes in about understanding the difference between induced subgraphs and just subgraphs. I claim that this is claw-free. But you might say, but wait, this right here sure looks like the claw to me. So are you telling me that that right there is not an induced subgraph of G and the induced from those vertices? And the answer to that question is yes, it's not an induced subgraph using those vertices. Recall that an induced subgraph, well, here, I'm going to flash the definition just on the screen for you. Let's, here we go. So this is all the way back. An induced subgraph. Given a graph G and a subset S of the vertex set, the subgraph of G induced by S, denoted by these corner brackets on S, is a subgraph of vertex set S and edge set, the collection of edges UV, such that U and V are in S and U and V is an edge in G. So the induced subgraph, the subgraph induced by S contains all vertices of S and all edges of G whose end vertices are both in S. Let's go back to our lovely example we were just looking at. Why is the claw not an induced subgraph of this graph? Well, what are you suggesting? You're suggesting that I pick these 4 vertices. So here, 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 and here. I see in my brain the claw right there, but if we've chosen those 4 vertices, and I say, yeah, the claw on those 4 vertices is an induced subgraph. Well, the subgraph induced by those 4 vertices takes every vertex, those 4, and every edge in G whose endpoints belong to the vertex set. That's this edge, this edge, this edge, and this edge. I am forced to include this outer edge here in my induced subgraph. So if I'm talking about the subgraph induced by these 4 vertices, I have to take these three edges and this fourth edge here. In fact, the way that this was drawn, essentially, to make it claw-free, these have to be included. If that edge is not included, if everything else in the graph remains the same, and this outer edge is not included, now this is no longer a claw-free graph, because the claw would be an induced subgraph of this thing. So including these outer edges exactly tosses away the claw as a possibility coming from vertices that look like that. Okay, so this is claw-free, it's 3 connected, and it's non-Hamiltonian. So the answer for k equals 3 is no. Upping the connectivity to 3 doesn't do it. But what if we up the connectivity to 4? Well, turns out that we have a theorem. So for k equals 7, we have the theorem. This is this was 1997. This was due to Rajacek. Probably mispronounced that name massively. So the result is if G is 7 connected and claw-free, then G is Hamiltonian. So upping the connectivity to 7 and just forbidding the claw was enough to force Hamiltonicity. So for k equals 3, the answer is no. For k equals 7, the answer is yes, it is forced to be Hamiltonian. What about the in-between? So here is conjecture. This is due to Matthews and Sumner. If G is 4 connected and claw-free, then G is Hamiltonian. This is still unknown. So this is still open. There have been some progress, some partial results. Not only is it still open in the case of 4 connectivity, I believe it's still open also in the case of 5 or 6 connectivity. So actually, this question is, this is from k is equal to 4, it's just this conjecture. This is open for k equals 4, 5, or 6. For k equals 3, it's false. The answer is no. And for k equals 7, there's the theorem that says, yeah, being 7 connected is enough. Okay, 7 connected and claw-free is enough. But this is open for being 4 connected, 5 connected, or 6 connected. Okay. So these are still unanswered. All right. One more open problem. This is called the path partition conjecture. So before I can actually state the path partition conjecture, I need to define a few terms, some notation. So recall from earlier today that tau of G we defined to be the detour order. which was the number of vertices in a longest path in G. Okay. Recall that given S, a subset of the vertex set of G, corner brackets S is the subgraph of G induced by S. That was the notation that we used. Okay. Given a graph G and positive integers A and B, if the vertices of G can be partitioned into two sets, A and B, in such a way that tau, that is the detour order of the subgraph of G induced by A, is less than or equal to little a, and the detour order of the subgraph induced by B is less than or equal to little b, we say that G has an AB partition. So this is the definition for AB partition. This is a little confusing until you see an example of it, because you're thinking of the detour order, which is the number of vertices in a longest path, in a subgraph induced by some subset of vertices, and you're putting an upper bound on that with these integers a and b. So what does this look like? Here's the best way of doing this, is looking at the following example. Okay, so here's the graph G. In these examples down here, I've given two potential partitions. Here I have a subset of vertices A1 and a subset of vertices B1. So my subset of vertices for A1 is ABCDHI. ABCDHI. And so the induced subgraph is this thing. The length of a longest path in that is 1, 2, 3, 4, 5, 6, right? The length of a longest path in the partition B, or the induced subgraph, or the subgraph induced by B1. B1 consists of vertices E, F, G, J, K, L. So E, F, G, K, L. So here's what I get. What is the longest path in the subgraph induced by B1? 1, 2, 3, 4. It's going to have 6 vertices. Sorry, I'm counting the vertices here, right? So here I think I was counting edges here when I started out, but I ended up counting vertices, so that might have been confusing as my finger was pointing around, but I'm counting the vertices here in the path. So in the longest path here, there's 1, 2, 3, 4, 5, 6 vertices. Here there's also 6 vertices. So for both of these partitions, or sorry, for both A1 and B1, the detour order for the induced subgraph of A1 and B1 is 6 in both cases. Okay, so for instance, that would not be a valid 4-7 partition, because the detour order would would fail to be less than or equal to 4. Okay. But if I look at A2 and B2 here, so I've chosen vertices C, D, H, I from here. So C, D, H, and I. There's my vertices. The most vertices in a longest path here is 1, 2, 3, 4. Okay. In B2, again, here I have the induced subgraph. This is A, B, E, F, G, J, K, L. So I have this. This is actually a disconnected subgraph. A longest path is this thing down here, this piece, which contains 6 vertices. So A2, B2 would be a valid 4-7 partition, since the detour order of the subgraph induced by A2 is 4. That's the detour order is 4, so that's less than or equal to 4. And the detour order of the subgraph induced by B2 is 6, which is less than or equal to 7. So this would be a valid 4-7 partition, but not a valid, but this one would not be a valid 4-7 partition because both of these, the detour order was 6 for both those induced subgraphs. Okay. Further, beyond that, we have the following question, which is if a graph G has an AB partition for every pair of positive integers AB such that A plus B is tau, the detour order of G, then we say G is tau partitionable. So going back to this example, here I've shown that there exists a 4-7 partition for this graph G. If I wanted to show that this was tau partitionable, the detour order of this graph is actually 11. 4 plus 7 is 11. But that's just a single sum, right? That's 4 plus 7. If I wanted to show that this was 11 partitionable, or this was tau partitionable, I would need to show that this graph had AB partitions for 110, 29, 38, 56, and 47, which I've already done. Okay. So I would need to show all of those things just to make sure you're understanding there, right? That is what I would need to show. I'd need to construct an AB partition for every A and B such that A plus B was the detour order. And the path partition conjecture this is sometimes called the PPC, states that every graph is tau partitionable. This is still a conjecture. Okay, this was first mentioned in 81. There's been a lot of progress, but it is by no means solved, so this is still unsolved. you'd be very famous in the world of graph theory if you could resolve this question. So every graph is tau partitionable. If that's not the case, of course, you would have to construct a graph that's not. So, if you're looking to investigate there, you might want to ask questions like, well, has this been verified for graphs up to some order, right? What's the smallest order graph for which this has not been verified, right? That's like the crudest possible starting point if you wanted to start investigating from there. There are some results, though. There's some progress here that kind of points to certain things. So here's one such result. I'm going to kind of summarize several results into a single theorem. So the graph G is tau partitionable if any of the following is true. So first thing, if the maximum degree of G is less than or equal to 3. Also, if the maximum degree of G is greater than or equal to the number of vertices of G minus 8. Three, if the detour order of G is less than or equal to 13. But also, if the detour order of G is greater than or equal to the number of vertices minus 1. So if the max degree of a graph is either very small or fairly large, then it's tau partitionable. If the detour order is fairly small or fairly long, then G is tau partitionable. So it's almost like this is sort of resolved except for graphs that are essentially mid in those categories, right? They are like, oh, it's like the max degree is not too small, not too big. The detour order is not too small, not too big. So it's these middle of the road graphs that are where there is some confusion. There's also the following theorem. This is from 2007. If G is claw-free, it is tau partitionable. So once again, forbidding the claw says something. In this case, not about Hamiltonicity, but about tau partitionability. Right? So in fact, in the same article that this theorem comes from, the authors also prove that in order to prove that the path partition conjecture is true, it is sufficient to prove that every two-connected graph is tau partitionable. So the PPC has been reduced to the two-connected case. Okay. So if you can prove that every two-connected graph is tau partitionable, that would show that every graph is tau partitionable. Okay, so of course, every, the way that mathematical development works is every single improvement on a bound somewhere, every single improvement making a theorem a little bit more focused, a result a little bit more focused, kind of zeroes in on the problem. Of course, all of that, sometimes the methods lead themselves to, they can be used further. Sometimes they can't. Sometimes it's just a matter of you're narrowing down, but the actual proof for the case you're interested in is totally different or completely off the wall. Sometimes that happens, but nevertheless, this is how progress typically happens, fairly slowly in this way. And yeah, so for the past 20-ish years, these results I've been quoting, and some of these results are from the 80s, and these things have not been resolved. So this is always good to be able to nicely state a few unresolved problems. And things like graph theory, number theory, and some other fields have the benefit of a lot of the conjectures, even the big ones, the important ones, are very easy to state and understand without too much extra knowledge. So that's the case here. You had to know a little bit about all the terminology we've built up in these few lectures, but once you know that, these are fairly simple to state, versus in some other fields, even just stating the thing can take there's a lot of background material that goes into even stating some of these conjectures, and it's certainly not as recognizable to someone outside the field as something like a twin prime conjecture, right, which is very easy to state compared to the Poincare conjecture or any of the other Millennium Prize problem type stuff. That's Navier-Stokes solution regularity stuff. Like that's a lot harder and more annoying to state. Okay, so that was just our brief detour, no pun intended, into showing you how just right beyond the reach of some exercises, one of those conjectures we made is literally just, instead of 2 paths, you increase it to 3 paths and ask about intersecting detour paths, and it was unknown. So like just beyond the questions we're asking in exercises that you're being asked to prove is like a substantial jump that you might not see until you actually sit down and think more deeply about these things. So that's the point. It's that to be honest, if I didn't tell you they were open problems and I just listed them along with some other problems you were asked to do in a homework set, you might not at first see that there's an issue until you sit down and actually try to do it, and then you can't figure out how to do it, and then you come and ask me for help, and I also can't figure out how to do it because it's an open question, and I don't know how to do it, or else I'd publish a paper doing it. So yeah, that's the point. Basically, I could sneak in any of those open questions, and you'd be, oh yeah, it's just another graph theory problem I'm being asked to do, right? You wouldn't immediately recognize it as, oh no, this is something way more mysterious. Okay, so I want to talk now about planarity of graphs. A graph being a planar graph. So let's imagine that we have 3 factions in a city, 3 rival factions. So we'll say there's the hyperdogs, the megacats, and the noble lizard folk. Okay. I will denote these as H, M, and N. Okay, the hyperdogs, the megacats, and the noble lizard folk will be denoted as H, M, and N. These are rival factions. They inhabit the same city. And in this city, there's not a whole lot to do. There's like a few things to do. So we'll say the city contains like exactly 3 things that we want to do. So we'll say that it contains a movie theater, an arcade, and like the restaurant quarter. That I will list as a single restaurant, but it's understood that this is in like a mega plaza. It's like a mall that is only a food court. So imagine a mall, but every store is food. It's just one giant food court. It's a food mall. Okay, that's what our restaurant is. So theater, arcade, restaurant. Those are the three things to do. Okay, maybe I call that T, A, and R, right? So here's my hyper dogs, here's my mega cats, and here's my noble lizard folk. And there are three things that they might want to do. They might want to go to the theater, they might want to go to the arcade, they might want to go to the restaurant, and that's it. These are the only possible activities that they could want to do outside of their own regions in the city. Okay. Now, all of them want to go to all of these at some point in time. So the hyperdogs want to go to the theater sometime. They want to go to the arcade at other times. They want to go to the one restaurant complex some other time. Similarly, so do the mega cats. And they want to do the same thing. Thirdly, noble lizard folk, known to enjoy their favorite arcade video games. So they also like to enjoy eating and going to the movies. So here we go. This is our graph. Now, you might notice that this graph is just K33. It's just the complete bipartite graph with partite sets of size 3 and 3. So that's what it is. But, so it's clear what the partite sets are here. But there's a slight wrinkle in this. So the whole reason of me phrasing this as rival factions is as follows. These rival factions absolutely hate each other, okay? And so they don't want to inhabit the same place at the same time. But also, you'll notice that in our graphical representation of what's going on here, it's hard for us to say when these are at the same location at once. But one thing I might say is these trajectories, if I thought of them as indicating some kind of motion through a geography, right? Intersecting trajectories would mean intersecting paths. I could think about that, even though there's no vertex where these things intersect. I could think about that as being still some kind of intersection that I want to avoid. So then the question is, can I draw this in such a way that the pairs of vertices, or sorry, that the edges intersect only at vertices, right? So question, can I draw this in a way that edges only intersect at vertices? Well, First of all, what is it that I'm even seeking? This seems like a little harder to do. Let's see some other examples first. So I'm not going to start with any of the easy ones. So like K1, K2, K3. A1, K2, K3 all satisfy this. So what about K4? So what is K4? K4 is the complete graph on 4 vertices. So let's draw it like this. There it is. Every vertex has degree 3. Every vertex is connected to every other vertex. That's K4. Okay, there it is. But two of these intersect at a point that is not a vertex. So can I change this? Is there another graphical representation of K4 that I could draw in a way that doesn't have this crossing, that is still the same graph? Well, what if I just took this and moved it outside? I'm connecting this vertex to this vertex. I don't have to pass through here, right? How about this? So how about these two are connected, and then these two are connected like that. Okay. So here, this is K4. This is the exact same as this. These two graphs are isomorphic, right? But I've now drawn this in such a way that all of the edges are present. They all represent exactly what they have to represent, but that none of them intersect except at vertices. Okay, let's do another example. So let's do K23. So here. Okay. Can you draw this in a way that this works for? So what are the problem? I don't like this intersection. I don't like this intersection, this intersection. Don't want them to intersect, right? Those are problem points. So what do I do? Well, don't have any problem here. If I draw this in and this here, I can't cut through here to go to that vertex. Maybe I draw this in. Now, what do I need to connect? So I need to connect this vertex to this vertex. This one is connected to both, and now this one needs to be connected to this vertex. Well, I can do this. Right? And that does it. So this is K23. Drawn in a way that none of the edges intersect except at vertices. Okay. What is it that we are doing? So if a graph G can be drawn in a way in the plane such that the edges only intersect at vertices, we say that G is planar. If it has no such representation, we say it is non-planar. A representation of a graph in this way would be called a planar representation of the graph. So in this sense, saying that a graph G is planar is saying that there exists a planar representation of G. Okay. Now, here's the assumption here when I label something planar or non-planar is that it's possible for something to be non-planar. But how would I show if something is going to be non-planar? So maybe I'll just write this question here at the bottom. How would I show G to be non-planar? You might say, well, why didn't you first ask how to show that G is planar? Well, because showing that G is planar is actually straightforward because, that's exactly what we did here in this example, where to show that the complete graph on 4 vertices is planar, all we have to do is exhibit a planar representation of it, which we did, right? So we did. There we just have to find one of these, right? So we have to find one. There it is. There's a planar representation, so it's planar. That's it. I don't need to look further and question whether there are more planar representations or anything like that. Same thing here for K23. To show that it's planar, I just need to exhibit a single planar representation. There it is. So showing that something is planar is a straightforward process. But if a graph can possibly be non-planar, how would I even know it? How would I be able to prove it? I would need to show that no such drawing of a graph, of the graph in question, can exist. I would have to show that every possible drawing of the graph in the plane, every possible representation of the graph in the plane, had edges that intersected at points that were not vertices. But I can't show that, like, that's a hard thing to do, right? There's no way that's practical to show that any possible representation has these intersections. So I'm going to have to use some like higher order technology here, right? And I don't mean computers here, because computers can also have hard times with these very things. So when I say higher order tech, I don't mean computers. I mean I need to use some sort of some invariant thing that is not going to be changed by changing the representation. So I need to know some quantity that is unchanging when I go from here to here. From here to here. I need to know like an essential quantity that is the same for both of these, or for both of these and for both of these. Right? I need an invariant of these sorts of changing. You want to call it a transformation going from here to here, however you want to call it. So I'm going to need something else. What am I going to need? So given a planar representation of G, a region in this planar representation is a maximal section of the plane in which any 2 points can be joined by a curve that does not intersect any part of G. Maybe I shouldn't use region here in the definition of region, so maybe I'll say maximal section, part of the plane, such that any 2 points in the region can be joined by a curve not intersecting any part of G. Okay. So a quick way of viewing this Here's just kind of like a canonical example here. If the G graph is on the left, the regions that this causes, this is a planar representation of G. The regions this causes look like this. It's like if you imagine this being a cookie cutter mold so that there's dough down. The cookies that result from using this cookie cutter on the dough, those cookies are the regions. Of course, there's this exterior region which goes off to infinity. That is, so it's unbounded in that sense, but this would be called the exterior region. We are typically going to talk about a region being bounded. So for instance, the region R1 in this example is bounded by 4 edges of the graph. The region R3 is bounded by 3 regions of the graph. So is R2 bounded by 3 regions, R3 bounded by 3 regions, R4 is bounded by 4, sorry, I keep saying regions, I mean edges. So R1 is bounded by 4 edges, R3 is bounded by 3 edges, R2 is bounded by 3 edges, R4 is bounded by 4 edges, R6 is bounded by 3 edges, R5 is bounded by 3 edges. R7, you might look at it as being unbounded because it goes off to infinity, but we would still call it bounded. We would call it bounded by the number of edges that it bounds. So in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Did I start here? So that is how we would compute the bound on region 7. We don't call it unbounded. It's bounded by all those edges on the outside of the graph G. Okay. That would refer to a bound number, or the bound degree. So the bound degree of a region R is the number of edges that bound it. Okay. So what does it mean to bound something? An edge bounds a region if it touches to, say, disjoint regions. Phrasing it that way is a little bit. We'll say an edge bounds a region R if it touches both R and another region R prime that is not R. This might seem like a very weird distinction to make, but basically here's the idea. So we say it bounds a region if it comes into contact with R in a region different from R. So let's look at this example. So, for instance, the edge E1 bounds nothing. It touches the region S1, but nothing else. We don't consider the edge touching the region at the vertex. E2 and E3, these edges only touch the region S2. So if you want to know what regions or what vertices bound S2, what edges bound S2. So the edges that bound S2 are this one, this one, this one, because each of those touch S2 and S1, and this one, this one, and this one, because each of those touch S2 and S3. Each of these touch S1 and S2. Each of these touch S2 and S3. Those bound, so those would be the bounds of S2. The bounds of S1 would be these 3 edges. E1 does not bound S1. E2 and E3 does not bound S2. E1, E2, and E3 don't contribute bounds. They don't contribute to the bound degree of these things, even though they are actual edges and vertices in this picture. Okay. And now I am going to show a picture, several cases here. So here's a graph. N is the number of vertices, Q is the number of edges, R is the number of regions. In this case, the regions are, I have an inside and an outside. Right, so I have an inside, an interior, and an exterior. So N equals 4, so that is the vertices. There's 4 edges, and 2 regions. Here, vertices, number of vertices is 7. The number of edges is 9. The number of regions is 4. 1, 2, 3, and then an outside. Those are my 4 regions. Here, number of vertices is 5. Number of edges is 7. Number of regions is 4. 1, 2, 3, and an outside. Here, the number of vertices is 8. The number of edges is 12. The number of regions is 6. 1, 2, 3, 4, 5, and then the outside. Here, the number of vertices is again 8. The number of edges is 12. The number of regions is again 6. This looks different than that, but are these two graphs isomorphic? You can think about that. Pause this and think about that. Here is another thing. You have 10 vertices, 9 edges, but there's only one region, just the outside itself, because this is a tree. But between all these different graphs, do you notice a pattern? Well, we'll get into it on Monday, but what is true about all of those things, we might as well go ahead and spoil it. That the number of vertices minus the number of edges plus the number of faces, we'll call these the regions, is equal to 2 for all of those things. This is known as Euler's formula, and I'll talk a lot about this on Monday. We can discuss kind of where this comes from, why this is useful. Again, the form that we're going to see it in first before we rephrase it for regular polyhedra, or just for polyhedra period, is this. So it is the vertices, edges, and the regions, if you like. Here, this F refers to faces. Why this works is that there is a number, that number on the left, the alternating sum of differing dimension objects, so 0-dimensional object minus 1-dimensional objects plus 2-dimensional objects. That alternating sum is called the Euler characteristic of the space in question, and that is one example of a topological invariant. It's one of the important examples of a topological invariant, and that is what is happening here. So there's an underlying topological invariant saying that for two graphs that are equivalent in some, or graphical representations, if you want to pass to that level, that are equivalent in some proper notion. Does that mean isomorphism? What does that mean? For two graphical representations that are equivalent, they're going to have the same Euler characteristic, and it's always going to be 2 in this instance. The reason why it's all 2, I'll explain that next time, or why it's always 2. But yeah, the good news is that in graph theory, or in the theory of polyhedra, this number is always going to be 2. And that has to do with that has to do with the dimension that we're in. That has to do with the 2D nature of it. So anyway, I will pick up here on Monday, and so I will post your third homework later today, and post an announcement when I do, so you don't have to be waiting around for it. So anyway, I think that's that for today's lecture. So I will see you all on Monday. Have a good weekend.